for this to go through. All right, so while this is happening, so Hamza is a potential postdoctoral fellow in our lab. He is a Ph.D. student right now in the Biomedical Engineering department at the Brno University of Technology in Czech Republic. And he develops data efficient and explainable deep learning models for medical image analysis and has published and presented his work internationally. He has had his research traineeship in Germany, Portugal, France, and wants to advance trustworthy clinical AI systems. Right, Hamza? Please go ahead.
Thank you very much. So, welcome everyone. Hi. The title of my presentation is Advanced AI for Medical Image Analysis. So, and I'm from Brno University of Technology. So, before going into the details, I have to tell you guys about myself. So I recently submitted my PhD in biomedical engineering, and my background is electrical engineering. So my research focus on making AI tools for medical imaging more explainable and clinically applicable. So, so now we are into the presentation. So when it comes to medical imaging, so we face a number of common challenges. So like, for example, for low contrast and noisy images, variation between different ultrasound, different scanners, not specifically ultrasound, and we have limited annotated data sets. So in order to cope these challenges, we develop the research objectives that are built and end-to-end AI pipeline that can robustly handle these challenges. So we want to use advanced data augmentation techniques like GANs and the diffusion models to expand our data sets. So ultimately, we want to ensure that the AI's outputs are both trustworthy and explainable for the clinical use. So then I will start these research objectives and explain these things. So, so let's start with the pipeline. So I built a UNet++ model for segmentation. So the UNet architecture is an enhanced version of the UNet featuring nested and then skip connections. This produces a very clean and precise segmentation marks to capture the fine details of the tumor. So once we done with these generated marks, we fed these marks into the feature extraction like feature extractor, which is MobileNet V2. In my PhD, I explore a lot of feature extractors like Inception V3, MobileNet V2, VGG16, and Efficient B7. So out of these, the best one. Okay, your email just I received. Okay, sorry. So. So the MobileNet V2 performs is better because in ultrasound we have a limited data sets. So it is the lightweight architecture so that can work well in the limited data sets. So it uses the depth-wise separable convolutions to reduce the number of parameters, which is ideal in our case. So after extracting these features, we fed these features into the, we convert these features into the vector form and then fed into the classification tasks. For classification, I use multiple classifiers and try to find how one classifier is better than the other. So these are the few results of the segmented masks and with the grade cam scans. So it's a grade cam is like kind of helpful in the clinics. So these results are published in IEEE Access. So these are the results of the classification tasks. So as you can see that ANN performs better than the other networks, and like the test accuracy, we are focusing on the we were focusing on the test accuracy. So the ANN performs better than the other architectures, other classifiers. So then we will move to the next thing, how we can cope up with the data scarcity. So for that, I went to Germany on the traineeship in the like second year of my PhD. So I work on the conditional GANs. And in conditional GANs, we can generate the synthetic images. So the best thing of the GANs or synthetic image techniques, that we can control the data set. That in real world, in real world, the malignant cases in our case are less than the benign case images. So we can control these images, and we can make the balanced data sets. So for that, we generate the images, and then we fed into the classifier, which is ultra GAN net classifier, and try to like see the results. So it has like you can see these are the generated images, but these are not a good quality because GAN is inbuilt unstable. So that's why these images are not like kind of a realistic. So and this is the confusion matrix of the ultra GAN classifier, and we get these results. Some malignant cases are like give the better precision recall and F1 scores, because uh, the model was built like this. If it sees that tumor or anything unusual, it gives the maybe false negative values. So this paper is under published, so under the review process. So let's see like when it will uh, accept, or when we get the reviews for this work. So then after that, in the last 3 months, in the previous 3 months, like I went to France for another training. There, I explored the diffusion, stable diffusion pipeline. The work they are doing is they are working on the drone localization and the smart traffic system. So they use the diffusion process in order to make the synthetic images using the text and the semantic masks. So they condition on the text. So when I went there, I like we discussed that we can generate the medical images using the diffusion model also. So we are in like in talks, and we like I generated these images specifically for this presentation, and these images you can see kind of closely related to the real images, and these images are just from the stable diffusion version 1.5, and today the latest version is 3.5. So I just want to show you guys how strong is the stable diffusion uh, for making the synthetic images. So this is quite powerful, and now we are in talks how we can synthetically generate the images, and we are making the storyline, like whether we need the image for generation, for image to image generation, or whether we need the biopsies for this. So like we are in talks, and maybe in 3 months or 2 months we will like write a paper and send to the top tier journal. So this is for the, I guess, stable diffusion. And my research collaboration is like in the previous year, I talked with the Harvard, one of the professor in Harvard, Peter Fried, and working on the EEG signals. Then I have a collaboration in Coimbra, Germany, and in Montpellier, France, and King Fahd Medical Hospital, and here Brno, and in South Korea. So that in this lab for like 3-year roadmap, first I will like adopt some adaptation and generative augmentation, and try to um, uh, like try to engage with the researchers in your lab, and try to like apply my knowledge and your knowledge uh, to make a good journal papers, transactions in IEEE. And then the second year, we'll do clinical collaboration, and we will write a grant for future fundings. And the like in third year, like I will maybe co-supervise some students and lead some kind of publications. So this is the research career direction that I am like looking for. I started my research in my master's in electrical engineering in Pakistan, where I use the MRI in order to find the cortical thickness to optimize the transcranial direct current stimulation technique. Then I use the ultrasound for detecting the breast cancer. And like, and from to 2026, I will like if I get the postdoc, I will apply my knowledge and try to implement my knowledge on the given data sets or given opportunities in your lab, and try to implement my knowledge on that. So if all things are smooth, and I'm like kind of optimistic, 2029 I will can maybe build my lab as an assistant professor, and then in 2035, like after that, the professorship. So this is my like very optimistic research career direction. So after this lab, so these are my publications. Three of them are first author. One is under review. One is the poster presentation, and one is published. And others are like secondary authors. So then I want like for the conclusion of this presentation. Uh, First, I tell you about how I developed the deep learning based segmentation and classification pipelines for breast ultrasound, specifically to spot early cancer detection. Then how we can leverage the synthetic images into the real world problems, and how can I make a contribute in your lab and make myself a broader and gain experience in your lab. So that's it for today's. Thank you very much. If you have any question, you can ask.